Go right ahead.
Here. All right. Hi, everybody. So, this first slide that you're looking at announces our title. This is an all-electric, passive house, domestic hot water design session. Kind of a class, we'll see. This development itself, this is built by Onion Flats, which is, some of you probably know, it's a leading passive house developer in the Philadelphia region. This is in Erie, California. Oh, sorry, California. I'm in California. Erie, Pennsylvania, right on Lake Erie. And so intensely cold, icy winds. When I was going to college, my first place I went to college is Bowling Green, Ohio, which we called Blowing Green because it's off of Lake Erie as well, about 20 miles, but still, it's just flat as a pancake in between you and Lake Erie. And oh my gosh, does it blow. So, passive house design, you guys already know all the envelope measures, so I'm not going to try to focus on that at all. I'm really going to go deeper into the mechanical systems. So, next slide. Here, this is me saying hello. Uh, I grew up on a farm in Wisconsin. My wife is a farmer. We have a ranch here of about 30 acres and hundreds of sheep and pigs and cattle, and I drink fresh milk from the cow every day, and trying to sort of imitate the back to the lander lifestyle that I was raised in rural Wisconsin. My parents had an organic farm and a successful in-town business of making jewelry. They own the jeweler's workshop on State Street in Madison. So came here. You see that house up there? That the house on the top, that is a 1932 house that was retrofitted from 1978 onward. It is the last demonstration house from the Carter era in the whole country. It was student funded, but founded by one of the Carter funded demonstration homes that was in Arcata. So when Reagan came into power as president, he canceled all of the funding for rebates and demonstration homes. And this was the only demonstration house in the country of hundreds that wasn't federally funded. And so it persisted. And that's where I was trained. I've been involved in that house for the last 25 years, learning how to install renewable energy systems and retrofits and such. Okay, I was a high school teacher briefly. You'll see there are these little tiny homes. This is the first it's not a subdivision, because it's actually an apartment complex of sorts. Each individual home is all one parcel. But this is a zero net energy, all electric, 26 homes. And it's the first one that succeeded in our country in actually getting more than 100%, like 100% plus offset, all electric houses. Every single one of them is a low income senior house, and they have like negative bills of $200. Now, this is zero energy ready homes. As you know, has more air leakage, but it has about the same insulation. Not nearly, as much attention, of course, to heat transfer, just simpler instructions. But, this is insulated slabs, R5 insulation on top of the walls, completely tested out with all HERS measures to being below 3 air exchanges at 50 pascals. And then below there, I'm going to do a little more detail on that, Hillandale Gateway, but that's an example of my biggest passive house development that we're supporting right now. It's 500 units. It's going to be 100% offset of one of the two wings. You'll see there, that's the senior one. We're going to do 100% offset of the 11-story building, and then whatever extra power is left over goes to the family units on the other side. All right, next slide. Here we are. We're in Brooklyn, New York. This is where my siblings live, except one who, after 20 years of being an artist, just fled and moved here to Arcata with his family because of COVID. And so I get my brother. So this is a townhouse, just like what my other brother develops all the time in New York City, and much bigger buildings too. It's passive house, just starting there. It's using a Stiebel Eltron heat pump water heater inside the residence, meaning it's pulling the heat from the residence. That residence is heated by a 3-zone heat pump water heater, and there's 3 flats here. Each are 1,500 square feet. So each one of them has 3 rooms or zones. So, and each one also has a 4-kilowatt system up on the roof for zero carbon offset. And on the right-hand side, you can see a ventilation system. Now, that's like a whole house type, the Comfo Air 350 by Zender. I just wanted to start pointing this out right away, is that in really cold climates, sort of the cheap way of doing it is to use a heat pump water heater inside the envelope. It doesn't need like fresh air. It just needs heat. And these are using R134A refrigerant, which generally doesn't go below freezing. So it wants to be inside of a warm envelope. Like in warmer climates, like in California, they're used year-round using outside air. But once you get into cold climates, you should bring it inside the envelope and then heat the air with a specialized cold climate HVAC heat pump, like what you're seeing there below. So that is the inexpensive, totally reasonable way of doing it. It'll chill a room about 1 degree over the course of a day. They run as a heat pump compressor, right? It runs between an hour to 4 hours a day, depending upon how much hot water you use, and also how cold the water is that's coming in, and if it's using cold outside air, if it's using tempered inside air. So it can run like an hour to 2 a day in a normal house. It will run for a while in the morning, it will run for a while in the evening during peak loads. And that is an affordable way to develop with a relatively inexpensive heat pump. I'm going to show you cold climate appropriate heat pumps also for water heating that go outside. But I just wanted to immediately introduce this is, I think, the best practice. Get an affordable heat pump water heater tank that's integrated, all done in the factory, just plug it into the wall, and use the inside of the apartment or house or whatever residence. Use the heat that's from a cold climate specialized heat pump, ones that go down to -20 and -30 Fahrenheit while still in heat pump mode and don't need electric resistance to perform in those temps. Now, I'd be happy to take questions as we go along. I'm a science teacher by training, so please unmute yourself and ask a question if you have one, and hopefully we have enough time. I don't have like an overwhelming number of slides because I want to solicit your questions around your own projects if you have any questions. With that, can you go to the next slide, please, Tony? Slide 4. Here, check this out. I am so impressed by the developer on Noon Flats, which is Tim McDonald, the architect, and his 2 brothers. And they design, that's Tim's job. One brother constructs, he's a general contractor, passive house specialist, and then the third sells, because a lot of these are market rate, but he also does affordable housing. And this project is exceptional. It's the most recent one they finished. It was built for, I think, $169 a square foot, all in. He generally can build passive house and zero net energy for the comparable price on the market just for standard housing. Because they're an integrated system, like there's no markup per se, and certainly not an exploitive markup between the brothers as they do their services to each other within one company. So as an integrated development organization, they can really keep prices down to just standard market rate prices. So what you're seeing here costs just as much as it would cost to build a standard code compliant multifamily building with no solar on it. And this is passive house. This is, I think he's done like 10 or more passive house. I mean, I think they've done almost 40 developments, but he started doing passive house preferentially and then exclusively starting around 2013, I think. But there was a recession to deal with, as you recall. And his cool stuff is arrested right now because of COVID. So he's not getting to build, they're not getting to build the next one. Now, obviously, you might be noticing that they have facade integrated solar panels on 3 sides of the building and the roof. So if you go to the next slide, you can see what that's like to live inside of. So up on the roof, there's a rooftop garden and the panels are the type that let sun through. They don't have like plastic melamine on the back of them to block sunlight. So that's called bifacial. And it means you have dappled sunlight underneath. And yeah, it's a grid. I'm not saying it doesn't, reflect the fact that there's solar panels above you, but it's certainly pleasant. And he has holes sort of cut into the roof to let large amounts of light through. I didn't point that out in the previous slide. So, Tony, could you go back to slide 4 for just a moment? If you see on the roof of the building, there are gaps. And those are essentially the skylights where the rooftop garden is that you're seeing. Now, if you go back to slide 5, you can see that. And then on the upper right-hand corner, you can see the inside of the apartment where you're looking out windows that have those bifacial solar panels. It seems pleasant enough. I've shown other people and they thought it was cool. you know, so you can make a choice about that, but it is cost effective. It does mean that he has 4 stories, pardon me, 3 stories of residence and 1 story of parking and commercial spaces. And he's also offsetting people's electric cars with this whole array of solar. So he's providing electric car chargers downstairs as well, and solar offsetting them cost effectively. Also, note in this kitchen that there is a hood above that induction range. And one of the things I appreciate about him is his attention to exhausting combustion waste. So if we go to the next slide, number 6, I'm trying to make a point here, and that is the point I'm making. Use them, because I'm holding in my hands the 12th Annual North American Passive House Conference Proceedings from Seattle, Washington, September 27th, 2017. And so there are 2 different studies of the impacts. So Ryan and Shelley Minotair, anyway, they wrote an article on page 83, the impacts of human activities on indoor air quality in a passive house. Basically, they proved, and there's another one here, it's proved twice just that you can't get the combustion waste out of your kitchen with heat exchangers. That strategy, which I'll show you other people use, right? But it does not exhaust the amount of waste that even 1 egg cooks, that creates the PM 2.5 particularly, that are from burning oils. And if you have a gas range, there's huge amounts of PM 2.5 from the gas range. But if you have an electric range, which I assume you're all using of one type or another, then you still have a fair amount of combustion of oils and humidity. And ERVs and HRVs have relatively low exhaust rates. They might be 20 CFM, 40 CFM, 80 CFM, but they're not actually what you need, which is about 250 CFM to get about 80% capture of combustion fumes. And as a consequence, passive houses that are using recirculating hoods or no hood, they continue to have unhealthy levels of PM 2.5 after just very small amounts of cooking for hours in the bedrooms. It's an issue. And I understand why so many passive house designers are trying to limit the number of perforations in the building, and just want to use the ERV perforations, those 2 vents. But it's not healthy. It's just not. It's not effective. It's not. Even putting the ERV right next to the stove does not exhaust that ventilation, that combustion waste effectively. It doesn't. So you have to make a choice about, doing another airtight seal around a vent and preserving the health of your occupants. And I know where you guys all stand on an emotional level, so I'm just trying to bring this forward. This is passive house literature itself, you guys' own proceedings. Okay, next slide. I think I've made that point.
Hey, Sean, quick question. Have you seen anything on the effectiveness of the recirculating ones? I haven't seen anything.
Yeah, they don't work. They really don't work. So they're trying to use a carbon filter, but they are not effective, and they're also called forehead greasers in the industry because they so profoundly do not work that they just blow greasy smoke in your face. And even to the degree that they do work, people don't change the filters in a timely fashion, and so they quickly degrade into not working at all from their best case not working well. So it's something to be avoided. It's a waste of money.
And have you seen anybody try to just ramp up the ERV on a
yes.
timer or anything?
So the proceedings here, they talk about putting it into boost mode. It's not effective. Boost mode might be 120 CFM, and it needs to be about 250 CFM just to get 80% capture. So there's a huge amount of research that's come out of Lawrence Berkeley National Labs that I've been involved with for a number of years now, doing peer review and bringing other researchers to discuss, and reading the proceedings as well. What is an effective way of getting rid of combustion exhaust, particularly for gas stoves, which are just downright lethal and the amount of formaldehyde they dump into our house. It's the #1 source of formaldehyde if you have a gas range, which I'm assuming none of you do. But if you did, that's what gives dogs leukemia and cats leukemia and children leukemia, is this heavier than air formaldehyde that comes off of gas stoves and puddles around in people's kitchens that you can't see and you can't smell, but you've seen animals floating in it, right? So the 125 boost doesn't work. That's what the proceedings, the past proceedings from 2017 documented. But that's also well documented by Lawrence Berkeley National Labs with all sorts of real hood monitoring, where they're watching vapor, with different kinds of cameras with different kinds of sensors on it, but they're basically able to clearly document that you're only getting like 30, 40% capture efficiency on a hood that's at 125 CFM, 100 CFM, which is code minimum, where there's places that have codes that require exhaust hoods, is 100, like Energy Star is 100. You need 250 to do a fantastic job, or at least an 80% capture efficiency, and an ERV is nowhere near close enough to the range or strong enough. And it's just been demonstrated in passive homes that that's how it is, that ERVs, HRVs do not effectively exhaust stoves.
Thank you.
So you're welcome. There's the science for you. So number 7, this says advanced HVAC at front flats, the Minotair. I had the opportunity to talk with the VP of sales, about this. He made sure I did not call it the Minotaur. Had to immediately stop me when I misspoke. The Minotair. This is an interesting, cool product because for passive house homes, you might have very low peak loads of heat, like 8,000 BTUs at peak of heating, which is only 2/3 of 1 ton, quote unquote. It's small. That's like a single head heat pump. It's like a slightly large window air conditioner worth of heating and cooling, 8,000 BTUs. So this is a ventilation system that its job is to provide the regulated amount of fresh air that also has a heat pump incorporated into it. And it's not just any old heat pump, it's an inverter-controlled heat pump. And an inverter is a computer. That's all it is. That's what it is. It's a computer. And so it's computer-controlled. It's a nicer, it's like less technical way of saying it. It's got a little computer in there that matches the amount of heat that it puts out into that ventilation air with the amount of heat that's being requested and the speed at which the speed of the compressor, so that it can capture heat from both the exhaust air and the outside air. So this system is incredibly efficient in the winter at heating the ventilation air. And should you have a nice passive house envelope and probably an apartment building, you'd have 8,000 or less BTUs, or a smaller home. This could be the entire heating and cooling system just using your fresh air ventilation system, which I'll say again, it does not include the kitchen exhaust. That is its own dedicated exhaust-only kitchen hood. That's the way it needs to get done for health. But this is perfect for low-load heating and cooling and ventilation, or ventilation, I should say, first, and then heating and cooling. And this is what Tim McDonald is using, and that crew, Onion Flats over in Philadelphia. That's what they're using in that building I just showed you called Front Flats. All of their buildings are called this flats, that flats. So Front Flats. The Minotair. So cool.
Can I ask a question?
Yes.
If you are introducing this 250 CFM dedicated kitchen exhaust hood fan, when it's running, where's the makeup air coming in from? Is it all just squeezing in from your airtight envelope, or is it coming through the fresh air duct that's connected to your ERV?
It's probably coming through your fresh air duct through your ERV. That's like, we've studied this question in other building science oriented developer I get to work with on passive house projects. We've been struggling, like, what do we do about makeup air? And of course, no one wants to put in like a fresh air 80 vent, just like a straight up hole in the wall with a MERV 6 filter. I understand. Like, it goes against the grain of what you guys are up to. So there's definitely mechanical systems that will open up vents with an electric signal. So you turn on your hood, and there would be a mechanically operated vent that would open and let in fresh makeup air, That's one strategy. So if you want to guarantee you've got balanced air at that moment, that's what you can do. If you want to be sort of like, you know, then you can rely upon the ERV, HRV system to be providing that additional air, or just sort of pushing it, like pulling the air harder through it. Or you can also accept that you'll be depressurizing your residence, and we'll be pulling some air in from the outside. Or that it'll stay pressurized, depressurized per se, and the next time someone opens up the door, it'll be resolved. Now, keep in mind, this 250 CFM fan, at maximum 100% of the usage in a household that actually cooks a fair amount, would be about 40 minutes a day. So we've studied hundreds of apartments that are Energy Star with large households, 4, 5, 6, 7 people in them. And the maximum that we see is people cooking for about an hour a day total. So what we found is that in most cases, the maximum was 45 minutes. And the average is about like 15, 20 minutes of cooking a day. That's what people are doing on the electric range and oven. So people are definitely using microwaves for some things, which are like basically disappear as a load. It's so small in the amount of energy it consumes. People are using toasters. People are using teapots, all sorts of things that are like countertop appliances that are still very minor energy users. So, and don't require ventilation hoods over them, the way that the amount of oil that you're burning when cooking food does require, and the food itself requires some kind of ventilation hood. So you have to ask yourself, like, well, what if they're only depressurizing their place 20 minutes a day? Is that okay? What if it was 40 minutes a day for like a lot of cooking? Is that okay? And keep in mind, people don't usually use their hood. So multiple studies of this have shown that people use their hoods at best about 50% of the time. They use it at some point while cooking. 50% of the time, and 50% of the time they do not use it at all while they're cooking. And of that 50%, they are using it at some point during cooking. Of the total amount of time that people cook, the time incidence, it's only about 30% of the time people are cooking. Of that, we saw like 40 minutes is the maximum cooking period. Of that, people are deciding to use their hood 10 minutes. In the real world, most people are using their hood 10 minutes in a day, if they're using it at all, on average. So it's not that much depressurization that you're trying to compensate for. Yes, it's a large fan. It just doesn't get used that often.
I have another question, if I could ask it.
Please, yeah.
So I guess with the Minotair, first of all, was the front flats, was it PHI or PHI US certified?
Hold on for a sec. Let me go to, let's see here. How would I find that out?
The reason is that I've looked on the PHI website, and they have a fairly good detailed analysis of the Minotair, or there's one or two other ones. They're called active heat recovery ventilators. And because they have no passive heat recovery, it basically has to be working in the heat pump mode all the time, or it doesn't heat at all or cool at all. And they found that it uses about 4 times the amount of energy as, say, a Zender or a passive heat recovery ventilator. So they're basically saying that it's almost impossible to certify to PHI using a Minotair. So I'm just wondering if you've actually got hard data on how much energy they use on the normal mode, on the boost mode, in heating and cooling, and since I'm calling from Canada, when it gets down to like minus 25 Celsius for 3 or 4 months of the year.
Right. Well, it does have no bottom, so it'll continue in heat pump mode all the way down to negative whatever. That was one of the things I was calling up, like, can it handle negative 25? It says, yeah, it handles negative 25 because it's using the heat from the exhaust air. That's like an important part. It has a high COP at very cold temperatures because it's pulling the heat out of the exhaust air. You know, that heat recovery function makes it uniquely, like a COP of 3.3 to 3.8 when it's negative 5 degrees Fahrenheit outside is incredible. There's nothing that performs at that COP other than the Minotair or A sewage wastewater heat pump, that's another one, like the Shark out of Canada, that produces that kind of COP in the middle of winter. So, but I guess what I'm going to ask is, I would love to have you email me that article, because I don't know. I was, you're giving me new information, and I want to read it and send it over to Tim and such, and I'd happily include you and anyone else who wants to be in a CC like conversation about it to see what we can learn.
Yeah, I would be interested in that.
All right.
Could you put up your LinkedIn, or I guess have the moderator put up your LinkedIn or your email address? And yeah, I can definitely send that over, because we're having the same conversation, and there's a fairly long article, and with PHI, it's seeming like it's difficult, but PHI or FIAS, the US version, is a lot more lenient, which I'm not disagreeing with, but I've also been having trouble just getting any technical data on the Minotair, like how much CFMs, how much energy is used, anything.
Right.
I just put my email in the chat. Is that what you meant?
Yeah. That'd be great if someone could put my email in the chat. It is my full name, Sean Armstrong, PM, as in project manager, or like the nighttime, Sean Armstrong, SEAN, Armstrong, PM @gmail.com. That gets to me. So does Sean at redbirdenergy.net. Both of those are the same place. But
that Shark product that you just talked about is one of my favorites.
Isn't it cool? Do you know Lynn Muller?
Cool.
Man, I want to give that guy a hug.
Yeah, actually, I know Corey Barraclough and the folks that were on the planning team, Aquatex, and there's a few other groups that were involved in the Victoria Island project, Dockside Green, and the Southeast Falls Creek.
Well, I regret, actually, I did not put in the Shark into this slide deck, and I should have, because they are a domestic hot water heater. It escaped me. But for everyone else, just so you know, what we're talking about is taking the sewage from an apartment complex or a house, but usually it's a bigger building, and then having a vault with a heat pump, heat exchanger. So it's not like touching the sewage, but it is making a very cold surface inside the storage tank to suck heat out of it. And then through that heat exchanger, you now have a very high COP, like 3.5 to 4.5, for making a central domestic hot water loop. And it's quite remarkable. And you can even like use an air conditioning function. So you're like air conditioning commercial spaces downstairs, and that heats the hot water, taking the heat out of the air and sticking it into the storage tank essentially, and then using that heat for the central loop. So you can get heat both ways. So the Shark, in its smaller version, the Piranha, just so y'all know. Let's make sure you keep on going. And the Piranha, which is the smaller one, like the 5-ton. So let's go to slide 8, because I do want to show this is important. This is the inexpensive way of doing it in Philadelphia. We're down in the basement. It's a sort of conditioned space. I mean, it's underground, so it's not conditioned per se. I shouldn't say that. The sort of like a ground source in a way, though. You have 2 tanks. One tank is heating water, and it's passing that hot water into the next tank, and the 2 of them together are working what's called series. And then it is going through a pipe and a pipe recirculation system. So what you have is a vertical pipe going straight up, right, through 4 stories of the building, with just an arm off of it each direction to like apartments. There's like a wet stack of apartments going up and down. And then when the pipe gets to the top, it turns around and it goes back down in the same insulated sheath. And in that way, it is giving heat back to the water that's coming in. And what it's not doing is giving heat to the rest of the world, because when you start circulating it along walls going between apartments, you start having it, dump heat into the outside world and into apartments too, but that's no help in the summertime. So in this way, you reduce the amount of heat loss by just keeping a very tight loop up, curl right back down in the same insulated sheath. And there's 4 sets of these throughout the basement, or maybe it's 6, I forget. But each one of these 2 80-gallon tanks together is handling 4 residences above it. And that's a common way that I design apartments, is to share 1 tank among 2 households, like a big 80-gallon tank stored at 140 Fahrenheit with the heat pump only mode, so we don't use any of this 15 or 30 amps electric resistance that it's saying there in red on that tank. That's all electric resistance there. It only needs about like 7 amps or so when it's running in heat pump only mode. So it's also very power efficient. Okay, so, and that's very energy efficient. You use about 1/3 less energy if you just turn off that electric resistance quote unquote backup, which is extremely rarely needed. It is their hair trigger about turning on electric resistance, having monitored almost 500 of these tanks for the last 6 years of various brands. I'm just saying, like, you don't need the electric resistance. To store it at 140 Fahrenheit, turn on the heat pump only mode, everything's awesome. Any questions on that?
Can I ask a quick question here? I mean, basically, every heat pump water heater is going to utilize refrigerants, right?
Yeah.
And so, you know, in the context of,
let me
like,
cut you off. I know where you're going. Okay. So
yeah, exactly. It's a drawdown question. It's the drawdown question.
Yeah, and I'm gonna detail CO2 heat pumps in a moment, but there's 1/4 of a pound of refrigerant in each of these tanks. If you were to take a screwdriver and just attack this thing and perforate all the pipes and let out the 134A refrigerant, which is the same thing that you have in your refrigerator, by the way, that amount of leakage of all the refrigerant is equal to 1 year's worth of methane leakage delivered to your gas water heater. There's a 3% to 5% leakage, but just assuming 3% leakage, if you looked at the climate change impacts of leaking, you're just using a gas water heater, which has embodied in it, a 3% distribution leak and mining. In that circumstance, operating a gas water heater, just operating it, not even including its combustion.
I was thinking about as compared to an anode cathode, just like straight electric.
Yeah. And you have to look at, there's 4 times as much energy being used by that anode, or a different way of thinking of it, it is 12,000 miles worth of driving extra electricity per year to use an electric resistance tank versus a heat pump tank. It's about 4,000 kilowatt hours, and if you drive like 3 to 4, it's 3 to 4,000 kilowatt hours, and that's about 3 to 4 miles per kilowatt hour. So it's somewhere about 12,000 miles worth of driving.
I know, because it becomes a game. Like if you can drive down the rest of your loads and still get like a net zero home using an anode cathode, that would seem to be a more sustainable approach than a net zero home with a refrigerant heat pump water heater.
Maybe, but it really depends upon your grid mix. Like if you're saying 100%,
right.
something like that, like, yeah, once we get there with 100%, so if you're on a hydro grid up in Canada, if you have like a nuclear power plant, electric resistance is totally appropriate for places like Washington, Vancouver, Alaska, a variety of places that have deep penetration of hydropower. Sure.
Yeah.
But if you're on like the national average in the United States is about 80% fossil fuels. And in that case, right now and into for the next 10 years or so, it'd be important to be using a heat pump. So I'd say like at least get a heat pump for the next decade, and unless you're in a special spot, right? And then around 2030, it'd be fine to use electric resistance.
Yeah,
from a climate change impact.
Yeah, I mean, I think we're speaking the same language. It's just one of those things. Like as we move more and more to the use of refrigerants, I think at the broad scale and in like every residential project, I think there's a really significant environmental discussion that needs to be had for the long term. So anyway, thanks.
Well, and let me get into the CO2 heat pump thing in just a moment here. Let's go to the next slide, number 9. This is Solara in Rotterdam, passive house, of course. Everything's passive house, just so you know. So Pete Skinner there, he's tested out multiple different types of cold climate heat pumps. None of them are the Sandin, which I'm going to show you in a second with CO2. These are all using 410A, which is very similar, about 2,000 times the impact of CO2. But if a sealed product like this only has a couple pounds of it, it's still very unlikely to release it into the environment and has a profound impact. Now, Pete Skinner, uses his solar array, a thermal array, up on the roof for about 8 months of the year exclusively, with a small electric resistance backup just in case. And then he uses this Arctic, which is the best of the 4 that he's tested for producing it's rated heat at super cold temperatures. This is upstate New York. The Arctic of the brands that he's tested, that's the one that like produces consistently the heat, which I want you to know that. That's the most ideal one for using this kind of application. So in the winter time, he runs the Arctic, and he heats up the same storage tanks. He has the same electric resistance, backup to do like a 10-degree temperature bump from 120 to 130 or higher if he wants to do a Legionella purge. So this is a strategy. Now to go to slide 10, this captures something important about how Pete Skinner is doing his work. He's only using like a 2 to 3 ton heat pump for 20 apartments, which is one of the most efficient systems in the whole country. And I study this nationally, and I'm a national presence on heat pump water heaters. So he is the most efficient system. And what you're seeing here is an example of what he did. This is a better illustration. This is where we're using 3/8-inch piping for most of what's being delivered here. People frequently use 3/4-inch piping, which has 4 times as much water in it as 3/8-inch piping. And you have to therefore purge 4 times as much water before you get your hot water. So it leads to a lot of hot water waste because you use your little bit of hot water and then you have this huge pipe full of hot water. Still, like it cools off, you lose heat. You're never getting your hot water quickly or efficiently. So using the standardized plumbing tables, just so everyone knows, Redwood Energy's YouTube site has a huge amount of presentations. I give a conference every 6 months where we detail how to do all electric design and all the efficiencies that you can move with that, and particularly domestic hot water. So anyway, these are 3/8-inch pipes that you're seeing. They're from a manifold, so there isn't a recirculation system. Everything here is within 50 feet, which we were calculating so people could get their hot water in like 5 to 15 seconds. And this is like the most efficient way you could do it. And it's very similar to what Pete Skinner is doing. Oh,
Another question?
Yeah, please.
Is that 3/8-inch enough for like a shower and a filling the tub, or do they do a bigger line from home run for the shower?
Super good question here. So if you look at a tub, it does have a 3/4-inch line to the tub only. To the showers, we have 3/8-inch lines generally. I'm sorry, to sinks, pardon me. All the sinks are 3/8-inch, and the tubs are all 3/4. If we'd had only a shower, we could have done 3/8-inch. But because we had a tub, we had to do 3/4 in order to meet the water volume, because water comes out like 4 to 6 gallons a minute out of a tub versus like 1.5 gallons out of a shower. Yeah, you can go watch a movie now. No, I'm giving a presentation. Sorry about that. Sorry. My 12-year-old son very kindly just brought me warm milk, but he always wants to talk also. Okay. So
is
that's
that
the deal.
Sean, is that essentially a PEX system then, typically?
It is, but that's not ideal. I prescribe copper. So in a different development, we are using copper to all the sinks, and we're using PEX to the shower and the tub. Because PEX leaches phthalates, plasticizers. Plasticizers make piping flexible, and slowly plasticizers leach into your drinking water. And it happens from day one. I can taste plastic in piping. I like to drink out of sinks, and I can taste the plastic in PEX piping, which is very disturbing to me. As my original training is as a biologist, and my brother got cancer when I was 16 and he was 21, and so I focused my biology education specifically on carcinogens, which that is a carcinogen that you're drinking when you're drinking the phthalates that are in PEX piping. So I try to focus people on go to copper for safety, as well as the fact that copper has less drag. If I can go to the next slide just to show something here, slide 11. This is an illustration of drag, like the friction. And you find that PEX usually has more friction because of the fittings, frequently have any little flanges on them that reduce the flow at the fittings, whereas copper does not, and water flows straight through fittings. So you can have less friction. This is an illustration of shower head friction, and I say specifically Moen and Kohler are the two lowest. and the low lines, the red dots and the green one, actually there's a few different Kohlers that we're testing there. These are ones that will deliver a nice strong shower, even when you have only 26 PSI pressure, whereas ones that are higher up, the water will come out in a dribble, and your pressure compensating valve won't help. It just will be a dribble. So we were running into that problem at Solara, where showers are coming out a dribble, and so we tested all the shower heads so we could figure out which ones worked as advertised. So that's my take home, Moen and Kohler. So what was your question? I apologize. I just wanted to finish that point.
Isn't it also about the swoops and the swoops versus elbows?
It is. So Gary Klein's been teaching you. Our lab, Gary's lab, is here at my property. And
I just put a link to Gary Klein's webpage in the chat in case everybody wants it. I love Gary Klein.
Yeah. So you can see Gary Klein's presentations. You can see our presentations with Gary, because I've been working collaboratively with him for field research for 6 years or so. So we have the testing kit here. Yes, swoops are terrific. It is not necessary, but it is absolutely terrific. So yeah, we should probably move on from there, though. But that's like how to make water go around corners with less drag. And we've been testing all different piping and such to figure that out. Okay, slide 12. Now this will satisfy the person who likes electric resistance water heaters. This project has electric resistance water heaters. So Bradford Station, you're seeing here, has a very cold climate appropriate HVAC system. So that Mitsubishi product up there, it's one fan coil per apartment. They do transfer fans in between bedrooms and the common area where it gets heated. And then they have like a 30-gallon lowboy electric resistance tank in each apartment. And I'm talking with the developer because he'd like to learn how to use heat pumps, but just didn't know. And I understand heat pump water heaters are only about 3% of sales in the United States, so most people have never bumped into one. But my development since 2008 have been all electric, 100% solar powered, and there's not enough roof space to do electric resistance water heaters and 100% solar powered unless it's just a one-story building. But as soon as you get to 2 stories and 3 stories, you need to move to a heat pump water heater because water heating is usually the #1 load in an apartment. Okay, so there you go. That's one in Michigan, Grand Rapids, cool project. Slide 13 is called Hillandale Gateway in Silver Spring, Maryland. So I sort of teased that one at the beginning. You can see this parking garage in the middle is covered in solar panels, similar to what Onion Flats is doing over in Philadelphia. This is in Maryland, right on the Washington, D.C. Beltway. And it's kind of cool. If you see on the right-hand side of the image, you can sort of see how an on-ramp is swooping around. That is the D.C. Beltway. I was really hoping they would get this built during the Trump administration because I thought it would be terrific to sort of show off an amazing solar power development on the Beltway. So just to showcase what all electric can do, which is mostly reduce construction costs, like as a nonpartisan thing. In our country, Republican developers, you might think, all over the country have settled upon all electric as the less expensive way to build, such that like the majority of water heaters since 1950 have been electric. The majority of space heating since 1970 has been electric. Like that's the #1 type. I should say the plurality. It's #1 fuel that gets used. 88% of all dryers sold in the country are electric, and like 65% of stoves are electric. So this is because electric is cheaper to build. And this is a great example. This is a very cost-effective builder who's also a serious building scientist. So we're talking about water heating. This is an example of where they're using these water heaters in the conditioned space in the hallways. So there's 1 tank per apartment, 40-gallon tanks for 1 bedrooms, 50-gallon tanks for 2 bedrooms, etc. 65 for 3, 80 gallons for a 4-bedroom. And each incremented bedroom gets like another 10, 15 gallons. There's a cold climate HVAC system for the hallways so that we don't chill the hallways. We're delivering heat very efficiently at like a COP of 3 to 4 in the wintertime. And then the water heaters are able to capture that heat at a very similar efficiency, like 3 to 4, because it's 70 degrees Fahrenheit in the hallway, maybe 65. And that's perfect for a heat pump water heater. It loves that temperature. So we have a very efficient system, and it's not expensive to build. Like these little hallway closets, that's not a big deal. And it provides a great service to the tenants. So this is like the most affordable strategy. Well, perhaps the way that sharing 2 tanks among 4 apartments, that's actually the most affordable strategy. I want to tip my hat to Tim McDonald. He was really good at cost-effective design. And there's also rooftop solar arrays and rooftop gardens that aren't illustrated on this drawing. It's a mixture of gardens and solar arrays on the roof. Any questions about that?
I have another one. Not to get, again, technical with the details, but when you enter these heat pump hot water tanks into PHPP, do you enter it in the 3.5 COP, or because it's inside your heated space, and in the winter it's basically sucking heat from your space heating to heat your house or to heat the hot water, do you have to use whatever COP or 100% efficient if you're using electric resistance to heat your house?
Well, it would be at the high COP. You know, when you transfer heat in, there's some inefficiency captured in the COP. And then when you continue to transfer heat, so you basically might lose about 10 to 15% of COP, coefficient of performance, its efficiency, by doing that double transfer. But when you enter it into the software, you should have a COP of 3 or greater, is how that would work in the wintertime. And assuming it's not like crazy cold outside. And it's rarely actually crazy cold outside. It's just sometimes it's bad.
Although I guess in smaller, this is more smaller residential. For big commercial, it makes sense. But for smaller residential, we often find that straight electricity and heat is the most efficient or cost effective. So then if the heat pumps inside, is the COP 1?
Yes. Yeah, exactly. If you're using electric resistance heating, then the lower COP, the HVAC one, that would be COP, correct. And in the summertime, interestingly, it would have a high COP and provide a little bit of free air conditioning. So if you had an air conditioner in there, it could, provide a little bit of that load. But when it chills the house, that itty bitty bit, that heat usually gets pulled inside. So it's sort of like free heating in the summer if you value the air conditioning. It's like free hot water because it provides this little bit of air conditioning load that you would have met otherwise. Okay, let's go to slide 14. This is large cold climate outdoor heat pump water heaters. So you see the Arctic, putting that front and center. Ice Air, which is a new vendor to me, but has gigantic heat pumps. I think it's out of Vermont. Nordic and Colmac. Colmac I know is Eastern Washington. I'm not sure where Normac is made. Nordic, I mean. So these are all heat pumps that are using the refrigerant called 410A, which is an HVAC specific one. The Colmac is mislabeled. That should say 410A as well. And you can see that all of them can go down to like -15, -13, negative temperatures. I'm focusing on the Arctic once again at the highest performance with this type of refrigerant. If you can go to the next slide, slide 15. Sanco 2 is the coldest of the cold. So on the left-hand side, you can see this is the type of heat pump that is it's called packaged, meaning the refrigerant doesn't leave the block, and it's carbon dioxide. So it's the lowest of all CO2 impacts. It's just CO2 itself. So it has a CO2 value of 1 versus, say, 2,000 climate change impact of 410A for the volume that it is. Keep in mind that methane is much worse just because of its leakage than any of these chemicals we're talking about. It's just so much methane leakage. Okay, so, and it's such a terrible climate change chemical itself. So you see how these 4 are arrayed. That's for an apartment complex. On the right-hand side, you can see the red line of the COP dropping. Okay, so you know as it gets colder, it stops being as efficient. I was saying earlier that like having a COP greater than 3 when it's really cold out is only possible with a few products, such as the Shark or the Minotair. So this is it's got a COP of 3 at 25 degrees Fahrenheit. And then the, I'm not sure what that green line is, but the blue line up on top, this is its capacity, meaning the amount of hot water it produces. And so this is producing exactly its rated amount of hot water, even as its COP is dropping. And its hot water production starts dropping only at about 5 degrees, only at about 5 degrees Fahrenheit. So it's rare that you're going to have any issue at all with hot water delivery. You should be able to continue to produce all the way through the most challenging of weather, just knowing that it's going to be less and less efficient. But it is a very low global warming potential heat pump, and it is the one that continues to do the best job at the coldest temperatures. It still has a higher COP and a higher heat output for the energy it's using. Its capacity. Okay, next slide, 16. You see the sand in there on the left-hand side. That's what the whole standard product for a house looks like, as opposed to ganging them up for apartments. But if you get a house type, these are for Japanese homes. That was their design for the style of bathing where you shower and then you take a bathtub. So they have 4 times as much heat production as any of the products to the right. They have a big old heat pump. You see that. It's a 15,000 BTU, 1.3 ton, whereas the rest of these over here are like 5,000 BTU, so a little bit less than half a ton of heating capacity. Eco 2, you can see it goes down to negative 30 Fahrenheit on the Sanco 2. The new light, which is just coming to the market, also has an inverter, so it does colder temperatures, and it goes down to negative 13. And it's using 410A, which is more the HVAC type refrigerant. And then these ones on the right-hand side, these are all hybrids. They're heat pumps with electric resistance backup, which I was recommending that you disable electric resistance backup and just run them at 140 Fahrenheit with mixing valves, or at 130 Fahrenheit and you don't need a mixing valve because it's safe. Let's go to the next slide, 17. Assuming you have one of these tanks, which I'm recommending that you put inside your envelope generally, this is how you do that. On the left-hand side, you can see if you have a big enough room, bigger than 700 cubic feet, you don't need any ventilation, like a laundry room or something like that. If it's big enough, just stick the tank in there, things are cool. Well, remember, they do have a fan and they have a compressor, so you don't put them in a laundry room if you have an electric resistance dryer, only if you have a heat pump or a condensing washer dryer, because the lint that comes off electric resistance dryers and going through the duct, that's terrible. And it fouls up the heat pump because it's pulling air through it. But this is passive house, so you guys probably are using ductless dryers, like a condensing washer dryer or a heat pump dryer, both of which just they just put water out of them. There's no lint that leaves them. Okay, so you can put this in a laundry room with a condensing or heat pump type. You can put them in a closet that has a vented door to the right of it. On the bottom, you can see you can put it in a closet with a small vent and then an undercut door. That's fine. To the right, you can see you can, on the top, you can exhaust or intake just through one duct or below there too. So depending if you want to pull air from the outside in or if you want to pull air from the inside out, or, those are for basements, those are for garages potentially. A garage is a great place to put a heat pump water heater generally if it doesn't freeze too hard in there, because you don't want your pipes to freeze. But these go anywhere where a gas tank goes, because gas tanks go, or gas products go anywhere where it won't freeze. And these heat pump water heaters, they have either electric resistance or a heat pump, and just as long as the pipes of water aren't freezing, it's fine. Number 18, unless there's any questions about 17, like where these things go. Okay, 18, what do they cost? Here you can see 1,650 heat pump water heaters, put in all of them actually retrofits, to be fair, so this is a little bit more expensive than new construction. So the purchase cost is like $1,100 to $1,300 for a 50-gallon tank. The all-in construction cost is $3,500 to $4,500. Sacramento is an expensive market, so in apartment complexes, the low-cost bid you might get is about $2,400 to install a tank, so twice as much as its cost. And they're not hard to install or anything, just like any other tank. So you just know that the $1,100, $1,300, that's what an on-demand gas water heater costs about. So it's not like it's more expensive than a so-so efficiency gas device. But of course it uses like 1/4 to 1/5 as much energy as a gas water heater. Okay, so that's its construction costs. I just wanted to see all the, you can see standard deviations there, by the way, and notice how high the price can get if you, like $7,000 for a rare few people who got really bad bids. And you can see on the bottom that it can be like $2,000 is kind of the low price that you'll get from someone. Not usually, but that's about as low as it goes. Maybe self-installing it for $1,500 is some of the low prices there. And my next slide is my last. Slide 19, these are geothermal / Geoexchange heat pumps. It's the same thing, just different names, same thing. They're unstoppable. You know, they can produce your heating and cooling needs. Whatever's going on outside is not important. They're sourcing their heat or they're dumping their heat into the ground, but they are expensive. So I don't encourage people to use them because I know that digging the wells and the holes and such, I've had it bid out. It triples the price, quadruples the price. They're not cheap, but they're very effective. And a version of these is the shark and the piranha that we mentioned, the sewage wastewater treatment, the sewage heat pump, the wastewater heat pump. And Lynn Muller, who were like talking about what a nice guy he is and such, he used to be the president of Water Furnace, which was one of these brands of heat pump, GeoSource heat pump water heaters. Or, well, they do HVAC and domestic hot water. So he used to be the president before it got sold out. And so he started his own company to do wastewater heat reclamation, which is super cool. And with that, I've tried to cover domestic hot water, HVAC, including ventilation specialties, and cooking, and some of the issues around solar. So you could see how advanced solar arrays are going. I think I did what I was trying to do. Do you guys have any further questions?
I have one more question. What's your thought on solar thermal? Is it still kind of dead for residential? Is other options cheaper, or solar thermal have a place?
Oh, okay. Well, you're asking my opinion, not other people's opinions. So I think solar thermal is dead. I've had to repair many solar thermal systems. I've found them to be, leak prone and very expensive when I try to do competitive pricing. So at this point, if you pair a solar PV array, like an electric array, with a heat pump water heater, that is by far the cheapest system relative to putting in a solar thermal array, which generally still requires a backup water heater, right? You can't just install a solar thermal. And so once you have to start getting a backup system to the solar thermal for wintertime, then you've raised the price compared to using just the heat pump water heater and a PV array. Because solar thermal is considerably more expensive than PV at this point. It didn't used to be the case, but PV's dropped in price so much because of the manufacturing of it. I mean, they make it in factories that don't have human beings now. Like robots build the whole assembly in a dark factory. Like don't have lights. It's just robots. So they're just incredibly inexpensive to build solar electric arrays these days, and solar thermal can't compete. Now, that's my opinion. If you asked Pete Skinner, he would strongly disagree, and he'd point out how solar thermal is free for him all summer, but he is having to tinker with that system all the time, trying to match solar thermal with his heat pumps and his electric resistance. But that's his job. He's a utility energy provider. He does a PPA, power purchase agreement, and he provides all the energy systems. So it's fine. He's an engineer. He doesn't mind tinkering and maintaining the solar thermal system and trying to integrate all the different controls. For my money, though, I have a different role in design, and I do affordable housing and such. So PV and heat pump water heater is the magic combination for pricing in my book.
Sean, we have another question from Melissa. What about for non-residential projects like a recreational building with locker rooms?
Well, for domestic hot water, I guess it's all the same. like, yes, you would use just a larger heat pump water heater, larger storage tanks, that kind of thing, say like a residential scale, and you'd put a PV array up on the roof. If you had a swimming pool in there, there's lots of swimming pool heat pump water heaters. The AquaQual Big Bopper is the largest, and there's lots of the heat pump pool heaters that will do like a 40,000 gallon standard backyard swimming pool, and the Big Bopper does 160,000 gallons. But you need about 4 of them for an Olympic-sized pool, which is 650,000 gallons. But that's not, like anything that was heating an Olympic swimming pool would be a large amount of mechanical equipment. That's a huge amount of heating. So, yeah, you do PV and you pair it up with a heat pump water heater, and you'd use the heat pump water heater. You just like figure out how to use it as opposed to trying to use it and integrating solar thermal with it, which has to be managed because dumping hot water into a heat pump water heater doesn't work very well. They rely upon the difference in temperature of cold water coming in, it being exposed to a hot surface to put heat into it. And if you bring hot water into and have it touch a hot surface, there's no heat transfer. And it makes the system sort of break. It's called short cycling. It turns on, turns off, turns on, turns off. Do I need to meet a load right now? Oh, I don't. And you just tear it apart, making it try to figure out if it's supposed to heat water at all these different moments when it doesn't need to. So then you end up turning it off so you don't short cycle it, and then you've got to manage it because not every day is a solar thermal good day. And so some days you have to turn on the heat pump. So I think just get the heat pump working, put a PV array up on the roof, and you're good. It's simple and effective, and you need the heat pump anyway for wintertime or electric resistance. But if you're trying to solar power your water heating, it's you can only go about 8 months of the year, almost anywhere except the tropics.
We have another question from Bill Lyons. Any noise considerations for heat pump water heaters in dwelling units?
Yeah, good question. So if we go to that slide, could we go back to slide 16, residential indoor water heaters? So Stiebel Eltron, that one's quiet. Rheem, that's quiet also. Like quiet, like a dishwasher running quiet. A.O. Smith, not as quiet. At least it hasn't been. I think their newest model came out quiet. When I say quiet, I mean about 49 decibels, whereas 55 decibels sounds about twice as loud, because of the nature of the exponentialness of decibels. So it's actually 4 times as loud, but your brain adjusts for it. So it sounds twice as loud to have 55 decibels. So it's good to get a 49 decibel one, and then it's as quiet as like any other appliance in your house when it's running. So you might want to put it in a closet so you don't notice it at all, but I think it would have been in a closet anyway. So yeah, really no issues. Like if you're putting it into a closet, the A.O. Smith is a little bit louder, but once you close the door, no big deal. And I'll say it again, I think that's used to be the case. I think that A.O. Smith has just made their machine a quiet one now. So I don't think you have any issues anymore with the current stock of heat pump water heaters. But if you are buying one, look for its sound and make sure you've got a 49 decibel one or quieter, just so that you can mess up that.
Okay. I just posted in the chat, this will be eligible for both FIAS and AIA credits if we can get them. The AIA is still pending, but if you email me your information and your AIA number, I will get you the correct information, as well as the FIAS CEUs. I will email out the appropriate information for that. And then I had a personal question about the geothermal ones. You mentioned that they are more expensive, significantly more expensive. Is that primarily driven by the cost of the wells or also the equipment itself? So maybe way to frame it. What's that?
It's just the wells.
Just the wells.
The heat pumps themselves are no different from any other heat pump. They're the exact same piece of equipment, really. I mean, pretty much. They are just a heat pump, no matter if they're an air source or if they're a ground source. It's the liquid that you're delivering to it as the heat source that's expensive, like getting that liquid down into the ground and warmed up by the dirt and then brought back up for wintertime heating and domestic hot water. So as an example, like you put in a heat pump water heater that's one of these standard residential tanks. You said like maybe it's 3,000, maybe it's 4,000, 2,500 to 4,500. If you put in the well to serve that, it's like $10,000 to $15,000 to put in the well that serves that ground source heat pump. So it's a significant cost add, you know, call it 10 grand at least, but probably 15 or more, because people often put in like 20 and 30 grand systems for bigger houses and such. It's kind of like a wealthy person's system. And it used to be the only system, and so only wealthy people were able to afford it. But now it's kind of like a perk. Like, why would you use a ground source heat pump unless you were in like central Canada and you didn't want to use some of the really cold climate air source heat pumps, which would still be cheaper. I mean, people use air source heat pumps in above the Arctic Circle now. You just have to get the right ones that go down to, you know, negative 30, and once it's below negative 30, you should be using electric resistance. You know, at that point, they're not making products that go below negative 30 yet.
So you could possibly argue that if your project has geothermal on it already, because that choice is made, that this might be an appropriate way to go, because you've already got the mobilization cost of the rig and the wells to be drilled.
Exactly. If you have it, use it. Super efficient system. Go for it. Absolutely.
And these, I assume, would work with pond as long as it's proper depth, etc. If it would work.
Yes, those are called water source heat pumps, but they are essentially the same thing. They just have slightly different settings and such. But a heat pump is a heat pump is a heat pump. It's just like, where's the energy coming from, and a water source heat pump like that, which is also what the sewage is. That's a water source heat pump. It's just warm sewage as opposed to a cold pond.
I think we already touched on this question, but I might reframe it a little bit too. So going back to the stove question, there was a question about induction. Do induction stoves have the same issue as gas stoves, which I think you already answered that they do. In terms of but you also mentioned gas stoves are worse.
Gas stoves are far worse. So all stoves cook oil. So if you were to cook on an electric stove, you'd get about 100 ppm of nitrogen dioxide and particulate matter. If you're cooking on a gas stove, you will exceed 100 ppm within about 15 minutes of cooking. And 20 minutes of cooking, you're at poisonous levels. Now you're at 200, 300, 400, 500 ppm of nitrogen dioxide, which is a very bad chemical for your body. It is definitely responsible for at least 1 in 10 asthma cases. Just the stove causes 1 in 10 asthma cases, gas stoves. That's real science published over and over and over from Mothers Out Front, from Lawrence Berkeley National Laboratories and UCLA, and just go down a list. The gas stoves cause asthma. And they also cause birth defects because the formaldehyde is a strong teratogen, which means, you know, it causes quote-unquote monster-like effects. It kills pets and little kids. You know, childhood leukemia is something that kills people within about 3 weeks. Childhood leukemia is a very fast-acting cancer. And formaldehyde causes leukemia. That is the #1 source of formaldehyde in your house, is your gas stove. And you're not going to encounter formaldehyde anywhere else in your life unless you're like a science lab technician that's, you know, pickling frogs or something. Otherwise, you're safe from formaldehyde except for your gas stove, which is the #1 source. If you are running an electric range, the code that's been announced for California, and I've been very active in this, right? The code now is that electric ranges need to have a hood above them that exhausts between 110 and 160 CFM. And 160 CFM is for the smallest apartments, because the less volume you have in your house, the quicker your air gets polluted. So that's electric stoves, 110 to 160. Science-based, now you're going over to gas stoves. You start at 180 and you go up to 280. That's the code. You can't even put in a range in California that's over a gas stove anymore that is the common type you find on the Energy Star product finder, which is like 110 CFM. Those are inadequate for gas stoves to protect people's health. Yeah, gas stoves are terrible. Get rid of it as soon as you can. It might have caused the premature birth of my twins. We were using our gas stove to heat our tiny little apartment, like open up the oven kind of thing. I deeply, deeply regret doing that because their premature birth was all sorts of problems. But I didn't know that nitrogen dioxide off your gas stove will cause a premature birth. I wish I'd known, because I was freaking stupid, to have done that. So, yeah, yank it out of your house, even if it's a gorgeous, beautiful old piece of dangerous, poisonous cooking implements. I had a beautiful stove. I had to get rid of it. I recommend that if you want to quickly do this, like you're hearing what I'm saying and you happen to have a gas stove, Eurodib is the best of the 2-burner induction ranges that you can just plug into any outlet in the kitchen. Eurodib. I've tested all the 2-burner ranges, and that's what I use in my own house. I never got a new 4-burner, 5-burner, whatever. I prefer to have 2 cooking stations in my kitchen so that my wife can cook and I can cook without us getting elbows into each other. So Eurodib is the best of the cheap, 120 volt, just plug it into any outlet ones. And you can certainly spend more money than, say, $200 on a 2-burner induction range, but then you get into like commercial class. The Eurodib is residential, lightweight. It'll last 3 to 5 years, before you have to get a new one like any highly used appliance does. Okay, sorry, I'll pause there.
So we are past the hour. We don't have any more questions rolling in, but I'm not sure if anybody else has anything. But I did want to, before we let people go, thank you. I found this extremely informative, so thank you for your time.
Absolutely. Thanks for having me.
Absolutely. So I will, I guess, take any last requests for questions, and then we will let you all go.
How about putting a heat pump water heater behind a fridge and letting them kind of talk to each other?
Yeah, the heat pump behind the fridge will produce, well, you can tell because a refrigerator uses about 375 kilowatt hours in a year for a good refrigerator, maybe 600 kilowatt hours a year for not so good, like larger, less efficient. The heat pump water heater will be using between 600 and 1500 kilowatt hours a year. So yeah, like putting it in the pantry next to the kitchen is a good idea because those two occupy essentially the same space. Putting your water heater right next to your refrigerator, well, like a little bit better, I don't think is meaningfully different, but you have then kind of a funky design. So, if it makes sense, yes, that's a good idea, but I wouldn't go out of my way to like save the extra kilowatt hours for doing that co-locating. And you could also put that heat pump water heater in a different area, but vent from the kitchen, like put a little duct. They can run a 12-foot duct off that fan. So yeah, that's a good place to capture heat is the kitchen. Absolutely.
Or your condensing dryer.
Yes, condensing washer dryers. If you guys don't know about those are awesome. You finally just put your laundry in and it comes out dry. It'll even text you and like your laundry's dry. And LG makes the biggest one that's available in North America. LG makes a 4.5 cubic foot one. All the other ones are like 2 cubic feet, and that's European style laundry. American style, 4.5 cubic foot is made by LG, condensing washer dryer. And yeah, definitely, that's a great place to co-locate.
Cool. Well, thank you again. And I guess I will, again, my email's up there if you guys want to get CEUs, or you can get me through the meetup page. Brent, I will send an email to you and Sean. Make sure you guys have each other's information for the dialogue about the Minotaur and Minotair, however it is. I'm already saying it wrong.
Minotair, they'll correct you.
Otherwise, thank you all for joining us. I appreciate it.
Yeah, thanks, y'all. Good luck making your all-electric passive house development. Best of luck to you.